While there is no fourth law of thermodynamics, there should be. It would state that energy is furtive and plays a shell game with nature. In cellular respiration, the trick is to find where useful energy is hidden. In the first 5 reactions of glycolysis, we follow the path from glucose, step by step, as it is split into a pair of 3 carbon molecules of PGL. For the second half of glycolysis, bear in mind that although everything occurs in duplicate, we're going to track only one PGAL. We'll watch PGAL synthesize ATP and energize a molecule of nicotinamide adenine dinucleotide, or NAD. NAD is one of a group of intermediate energy carriers, which is used to generate ATP. Its complex structure is devoted to the transfer of energy. Here within this carbon ring, the positive charge represents an area of electron deficiency and drives NAD to snap up a pair of energetic electrons together with a hydrogen ion. In this form, the energized NAD molecule is called NADH. For simplicity, we'll represent the electron-deficient NAD as NAD+, and the electron-rich NAD as NADH. Now let's return to glycolysis. In reaction 6, NAD+ saddles a molecule of PGAL. And with the aid of an enzyme, NAD+ picks up 2 electrons and a hydrogen ion. The product is an energy-rich NADH. In this exchange, PGAL grabs a free phosphate to form diphosphoglycerate, or DPGA. Let's pause and look at the energy profile. Over the first 5 reactions, energy was cranked into the pathway. Now, in reaction 6, some of the energy of PGAL is shunted out of the pathway in NADH. Charged with 2 energetic, shall we say ambitious electrons, NADH is an excellent energy carrier. Recapping chemistry, PGAL, having released electrons, is oxidized. And NAD+, having gained electrons, is reduced. So oxidation reactions release energy, while reduction reactions store energy. Reaction 7. The molecule of DPGA encounters ADP. A phosphate is transferred to form ATP, leaving behind phosphoglyceric acid, or PGA. From here on, glycolysis is devoted to eking out just one more ATP molecule from the single PGA. On its own, ADP lacks the necessary energy to capture the phosphate, so a subtle rearrangement of the molecule occurs. Then in reaction 9, a molecule of water is lost, leaving phosphoenol pyruvate, or PEP. The bond holding the phosphate is sufficiently weakened, so that in the final reaction, ADP liberates the phosphate and makes the ATP we sought, and the 3-carbon compound pyruvate. Again, let's step back and place all these reactions in profile. Two molecules of ATP infused energy into the system. From there on, energy was extracted by two NADH molecules and 4 ATP molecules. So what was the net gain? 2 ATPs were consumed, 4 were produced. The net gain was 2. Of the energy contained in the original glucose molecule, these 2 ATPs account for only 2.2%. The bulk of the energy is distributed between NADH, pyruvate, and heat. With a 2.2% payload, glycolysis in and of itself doesn't seem like a very effective engine. But when it comes to simple organisms like yeast, it just about gets the job done. These organisms survive. More so, they thrive with just a modicum of effort. Let's see why. Return to reaction 6. PGAL donates electrons to NAD+. But yeast has a very limited supply of NAD+. So if the last of the NAD+ were used to make NADH, glycolysis would grind to a halt, and absolutely no ATP would be produced. Yeast then resorts to a further strategy. It offers up its pyruvate. Carbon dioxide is removed, forming acetaldehyde. Next, NADH converts acetaldehyde to ethanol, common alcohol. This reaction produces NAD+, which feeds back into reaction 6 and continues to synthesize ATP. The extra steps that yeast took is called alcoholic fermentation. For simple life forms, glycolysis, together with alcoholic fermentation, satisfies their simple needs. However, higher life forms have to squeeze a lot more energy from NADH and pyruvate to enjoy the good life. In the next program, we'll examine the mechanism for extracting even more energy from pyruvate.